Lesson 9.1, Polygon, Angle, Sum Theorems. Introduction to polygons. A polygon is a non-overlapping closed shape composed of line segments connected at their ends. You have a more formal definition talking about coplanar segments and each segment intersecting two other segments at one endpoint. So looking at the list below, the question is which below are polygons? The easiest way is to look for things that fail. The sides of a polygon have to be segments. They cannot be curves. Do you see any of these figures with curved sides? Because of that curved side, it is not a polygon. Okay? The next piece that we're going to look for is it has to be a closed figure. So do you see any that would be open? Right here, this is going to not be a polygon because it's open. The last piece, it says that if you look at your definition up here, it says that they have to be non-overlapping. So if we look at this, the one in between the two that we just looked at right here, because it does overlap, this is not a polygon. You can make the case that it's two smaller polygons, but it's as one figure, not a polygon. All the rest of these shapes do fit our definition of a polygon. Polygons can be classified as either concave or convex. Formally, it's convex if and only if no line containing a side of the polygon contains a point in the interior of a polygon. So basically what it's saying, concave, we kind of look for it to be caved in. Using the formal definition, if I look at this polygon here and extend this side, it goes inside the polygon. That's what makes this a concave polygon. Okay? You can also just kind of look for a side to be caved in. So this would also be concave. There should be one more that's concave. See if you can identify that. Hopefully you found this one. The other three are convex. Easiest way to think of convex is it isn't concave. All right, so let's move on now and talk about polygon angle sum theorem. Basically what this says is that any polygon can be broken into a series of triangles. So if I took one vertex and drew a diagonal, if you notice what I've done is taken that quadrilateral and created two triangles. I can do that with the figure right here, choosing one vertex and drawing all the diagonals that I can. It separates my figure into triangles. You try the last one. Separate that into triangles. So let's look at all the good information that gives us. If we look at the chart below, we can track patterns that we see in the polygons and their angle measurements. All right, so let's talk about first a triangle. We didn't draw one above, but we know what a triangle looks like. It has three sides, and because it is a triangle, it has one triangle. We know the total degrees of the interior angles in any triangle is 180 degrees. So let's look at the quadrilateral up here. We separated that and it created two triangles. So our quadrilateral has four sides and we got two triangles. Well, the total degrees of the interior, if we look at our triangle, I know that this one has 180 and I know that that one has 180 degrees. So total we have 180 times 2 or 360 degrees. So our next one would be our pentagon. Pentagon has 5 sides. And if you look at your pentagon here, we have 1, 2, 3 triangles. 3 times 180 is 540. So we have 540 degrees. And our last one up here is a hexagon. Hexagon has 6 sides. Hopefully when you drew this, and you should have this one drawn, you found that you had 4 triangles. So what we should be doing here is 180 times 4, and so we're going to get 720 degrees. So let's look at how we can use this to find the total degree measure of any triangle. So we look at our patterns here, and I want you to look at the number of sides and the number of triangles and see if you can identify what's happening. Hopefully what you're noticing is that the number of triangles that you form is always going to be 2 less than the number of sides that you have. 3 minus 2 is 1, 4 minus 2 is 2, etc. So then think about the process that we did to come up with our degree measure. Once we knew how many triangles, we just did the number of 180 times the number of triangles that we created. What this allows us to do is come up with some formulas. So if we call n the number of sides, then the number of triangles has to be 2 less than that. So that's going to be n minus 2. Multiplying by 180 gives us the formula 180 n minus 2 to find the total degree measure in any triangle or any polygon. That's an important formula that you will need to know. So let's move on and talk about the exterior angles. You already know what an exterior angle is. It's an angle formed on the outside of your figure. And it's formed by extending one side. You're seeing a nice graphic here of some exterior angles. You should take a minute, pause the video, and go look at these 2 links. They show you a good animation of your exterior angles and help you understand why the sum of the exterior angles is always 360. In the pictures here, you can kind of see us taking this hexagon and shrinking it down, but those exterior angles are always staying 60 degrees. It's getting closer and closer to a nice, pretty, perfect circle. So what we find is that the exterior measure, or the exterior angle of a regular polygon, is just 360 divided by the number of sides. The word regular is important. This means that all the sides and all the angles are congruent in your figure. So let's do an example here. Let's take an octagon. How many sides does an octagon have? Hopefully you know that would be 8. So if it has 8 sides, then we know that the sum of the exterior angles is 360. So one exterior angle would be 360 divided by 8. And that comes out to be 45 degrees. So every exterior angle on a regular octagon would be a 45-degree angle. So let's see how we can apply this. On the next page you have a chart. When you come to class next time, this chart should be completely filled in to get full credit for your notes. We're going to go through several examples together just to make sure you know how to do each kind of line. So let's start with the top one. This is an n-gon, meaning we don't know how many sides, we're just formulating a general plan. So the number of sides in an n-gon would be n sides. So the sum of the interior angles, we're going to use the formula that we just developed. We just talked about that needing to be 180 times the number of sides minus 2. That's n minus 2 is our number of triangles. So then to get to one interior angle, so this is the sum of the interior. One interior angle, I would just take the total, that sum that we just calculated, and divide by the number that I have, which would be n. So I come up with a formula 180 n minus 2 over n. And the last column, we want the measure of one exterior angle of a regular polygon. We talked about that one as well, and what we need to do here is take 360 and divide by the number of sides. So let's go through and do a heptagon. How many sides does a heptagon have? Well, hopefully you know that's got 7 sides. So once I know that, I can calculate this by doing 180 times 7 minus 2. When I do the calculations here, this is going to tell me that there's a total of 900 degrees inside a regular heptagon. To figure out the measure of one interior angle, I'm going to take that 900 and divide by 7. that's not going to work out evenly, so we're going to say that that's approximately equal to 128.6 degrees. And our last column is the measure of one exterior angle, so we're going to take our 360 degrees and divide by the 7 exterior angles that we have and get that to be approximately 51.4 degrees. Feel free to stop the video and go do your lines for your quadrilateral and your polygons with 5 and 6 sides. Your name on each one of these, if it's got 20 sides or less, you should have a specific name for it. If you don't know the name, you have the power of the internet to figure that out. Okay, so let's move on and look at something a little bit different. Let's come down to this line right here. In this line, it's a little bit different. They've given us not the number of sides this time. What they've given us is the total degree measure, the sum of the interior angles. So we're going to have to work back and find n before we can work forward. So what I'm going to do is I'm going to take this and think through what is the formula that corresponds to this. So really, I'm looking all the way up here, and I can use this to set up an equation. I'm going to scroll down to the bottom and do this off. Actually, I'm just going to add a page in here, and we'll do it off to the side. So in this case, what we would have is our 180 times n minus 2 equal to 2,520. And now all I need to do is solve for n. So I'm going to go ahead and distribute. And then I'm going to add the 360 across. And finally, I'm going to divide and find out that that polygon has 16 sides. So when I look at this row, I know that this is 16. So now I have to come up with a name for a 16gon. This is called a hexadecagon. Once I know the number of sides, I can use my formulas moving forward. I'm going to take that 180 n minus 2, which they gave us is 2520, and divide by the number of sides. So this comes out to be 157.5 degrees. For my last column, I can do my 360 divided by 16, and I'm going to get that to be 22.5 degrees. Good? Okay, so let's move on. If you want to stop the video and do ones like those, the 3 that are right there where you have your some of your interior angles, that would be a good idea because they're all going to be worked the same way. So now let's move on and look at the next group. And we're going to go do this problem right here. So again, I want to look at this 150, and I want to pay attention to the formula that develops it. It's going to be all the way at the top of that column, and that's what I want to solve. So what I'm doing now is 180 times n minus 2 divided by n, and that's going to have to equal 150. So to solve this, I need to distribute here, and I'm also going to multiply by n to move that across. So I have 180n minus 360 equals 150n. Subtracting 180n gives me a negative 30n. So when I divide, I'm going to get 12. So all the way back down here, I now know that I have 12 sides. 12-sided figure is called a dodecagon. And now we can simply move forward. We're going to do 180 times 12 minus 2. 12 minus 2 is 10, so this is an easy one to do in our heads. Just going to be 1800. And then you can go over here and calculate your 360 divided by 12. The last grouping are ones where I'm giving you your 360 over n. You can work these the same way. So if I know this is 360 over n, then I can set that equation up and go solve. So 360 would be 20n, and when you divide comes out to be 18. So we've got an 18-sided figure here, and you should be able to go through and calculate all the other columns. If you don't know the name, look it up. If it's over 20, you can simply call it by that